Hello and welcome to this video tutorial on how to conduct a chi-square goodness of fit test. By the end of this video, you'll be able to create a chart showing observed counts and expected counts of a categorical variable. You'll be able to take the differences in those counts and, similar to finding a t-score or z-score, determine if the value is so large that you will be willing to reject your null hypothesis. In the last chapter, we learned how to find the confidence interval and conduct a significance test for two proportions. Notice that we are measuring the difference between the two proportions. What happens if we want to compare more than two proportions? But if we have multiple categories that you wanted to compare to existing proportions to what you observed, how would you do that? We want to see if our sample fits what is predicted. Take, for instance, the blue M&M project that we did earlier this year. Would you want to test all of the colors, one color at a time? Probably not. A chi-square, and it's pronounced chi like K-Y-E, distribution enables us to look at multiple categories all at once and determine if the observed values are what we expect them to be. The type of distributions that we see here is often used in fields of study such as genetics, where the laws of probability help us predict outcomes for each category. How many of you remember the Punnett square from biology, as seen below? The example you see here shows the possible genetic combinations of eye color for the red-eyed fruit fly, say that 3 times fast. Using a table such as this allows researchers to predict how offspring will appear in large sample sizes. Since we are conducting a significance test, we should first consider what our null and alternative hypotheses would be. We could write them out in the long way and show each proportion, but that would be very, very tedious. For chi-square distributions, it's proper and accepted by College Board to write out the null and alternative hypotheses in words. In a goodness of fit test, our null hypothesis will always be that the distribution is correct for all categories for what was given to us. The alternative hypothesis is always worded that at least one category is not correct. And I'll say that again, at least one category is not correct. In this case, we are looking to find evidence that the distribution claim from M&Ms is not the same. How far from their claim would you accept, what would you accept before you concluded that their percentages were incorrect? As we have seen from in the past, our observed counts come from the actual observations of your sample. So when you open up the bag and pour them out, what we see is our observed counts. To find the expected counts, simply multiply the number in our sample, in this case your M&M's bag, times the percent given to us by the M&M's company. For this example, suppose our bag had 60 M&M's. I recommend putting the percents in list 1 as you see here, and multiplying list 1 by 60, that was the count in our bag, to get list 2, as you see here. Now go ahead and put your observed counts in list 3. Note that while the observed counts are always whole numbers, the expected counts can be decimals, so don't try to round them to fewer than 4 decimal places. And just by looking at this, which categories, looking at list 2 and 3, appears to have the greatest difference between observed and expected? If you said yellow, then you're correct. The formula for finding the chi-square value is very much like finding the value for the variance that we learned earlier this year. Be careful when calculating the chi-square value for goodness of fit. Students often try to take shortcuts or not write down each component, and it's easy to make an arithmetic mistake. Very often on the AP exam, you'll be asked which category has the greatest effect on your decision to reject or fail to reject H0. In this case, yellow, as you said before, would have the greatest effect. And you can also verify this by looking at which component in your chi-square calculations contributes the most to your overall chi-square score? Once again, it would be the yellow component at 2.519. Have you thought about why we divide by the expected value when we calculate the chi-square value? Consider the following. Which will be more surprising, getting 18 blue M&Ms or getting 12 yellow M&Ms? Well, when you subtract 18 minus 14.4, you get 3.6. When you subtract 12 minus 8.4, you get 3.6. So the difference between each of the observed and expected for the blue and yellow are the same. But which fraction is greater, 3.6 out of 14.4 or 3.6 out of 8.4? Ah, now you see it. Now that we have a chi-square value, what does it mean? It still has similar meaning to standard deviation, except we're looking at the difference in observed and expected counts. Although this definition says that the distributions are skewed to the right, and chi-square distributions are always skewed to the right, as the number of categories increase, the density curve appears more and more normal. Although it will never completely be normal, it will always be slightly skewed to the right. Note that the degrees of freedom is found by subtracting 1 from the number of categories. If this were a standard t or z distribution, 5.8215 standard deviations away from the mean would give us a p-value of nearly 0, but chi-square values are typically larger numbers because they're the sum of all the categories, the differences of all the categories. How many degrees of freedom did we have with this example? If you said 5, then you're correct. With a chi-square value of 5.8215, would you reject or fail to reject H0, and at what level? Well, we follow the row of 5 degrees of freedom to where 5.8215 would fall, and then we go to the top and find the upper tail probability that's to the left and to the right of 5.8215. Now, at what alpha levels would you reject or fail to reject your null hypothesis? Obviously, the 5.8215 is very much to the left of the 0.25 upper tail probability. So it's actually greater than 25% probability of this event occurring. We can see that we would fail to reject H0 at the 10% level, and it would fail also, obviously, at the 5% level. Now you may state both in your answer, but choose one in your conclusion. 5% and 10% are more reasonable than the 25% to state in your conclusion. So in this particular case, I would say, based on my chi-square value of 5.8215 and 5 degrees of freedom, there is not enough evidence at the 5% level to reject H0. So I conclude that the distributions of M&Ms are correct. Thank you for viewing this video. Please refer to the textbook in Chapter 13 for more examples of goodness of fit tests. I hope that you feel comfortable about the two objectives that we presented today and your ability to evaluate a chi-square distribution. Thank you very much.